Well, here we are again. We had this equation. We just managed to explain where it came from. There it is, right there. Equation for the voltage. But it's not really very intuitive as it stands. And we'd like to be able to solve it. And what do you think would be the best way to go, Sam?
Yeah, I mean, this form looks vaguely familiar, but can you make it sound more familiar to me? Show me how it's done, Matt.
Yeah, so what we can do is we can pretend that I'm a wave and I'm pushing you, and then you reflect off the wall and come back. So we have waves in two directions. So we know from previous analysis that the general description of the wave will be a forward wave, and that was me pushing Sam, so that's F1. And you can write it in many forms, but we'll write it like this. And that's going to be the wave traveling to the right, and then plus a wave going to the left. So it's going in the opposite direction. So when I pushed Sam, I was pushing him to my left. That's F2. Then he hit the wall and bounced back, and F1 models that. So this is a forward traveling wave to the right and a backward traveling wave to the left. And in general, you have combinations of both. And you can easily see by calculating that it satisfies this equation. So normally we write this as V plus V minus. So this is
nice and concise.
Nice and concise, plus forward minus backward.
Great.
So that's voltage. So we're done, are we?
Well, what about current?
Oh, let's do current. Okay. Well, we could write the current equation down, but why don't we use the equation we got from the transmission line from KCL, di dt, or KVL rather. So,
C?
no, it's KVL.
Okay. Oh, right. Yeah,
right, di dt, because L was with di dt.
Good.
And the other I, so it's the voltage equation that we're using to get the IDT. And then we'll do something with I to get I, because we know what V is. So all we have to do is just do this. We got V as forward and backward waves. Go in here, differentiate with respect to Z, and then we'll have to integrate with respect to t to get I. So let's just set it up. Explicitly set up, right? So we know what V is.
Well, we have V here already, right?
Right, so we know that this is F1 of t minus Z over V plus F2 t plus Z over V. And there we are. Now we just have to differentiate this using the
chain rule.
Chain rule. And then integrate with respect to time. And if we do that, we will get I. Oh, by the way, this is a homework exercise related to the video. We're not going to fill in all the missing steps. I of Z and T is equal to 1 over L, the inductance, times the velocity V divided in the bottom, and then multiplied rather by F1 of t minus Z over V. Now here's the thing that you absolutely have to remember. It's not a plus sign. That's what you have to show.
That's what they get if they do the chain rule.
If you do the chain rule properly and the integration, that's what you'll get. And the units, these have units of voltage, so this better have units of impedance.
You're right.
Right? Otherwise, we're going to have trouble. Right? So that better be having units of impedance. In fact, it is. We know that. So this is something that we'll look at later, but it's coming in here. So when we do this, the basic things to remember is there's this factor in front, LV, not just plain old this stuff. There's a factor that has to take into account that we're dealing with current. That's impedance. And then this thing here. So it's not the same sign. And all the stuff we do about transmission lines, for lossless lines, in this form carries through, and then we're going to have applications. This is a must know, and it sits right here. And it's written as I plus, and this is a bit confusing, plus I minus. So
the negative sign is embedded in the I minus.
The negative sign is embedded in the I minus. So that's it. We now have solution. We have interpretations. We have the scaling. Everything is set for any application that we want to do for lossless lines.
I wonder if they'll get tested on this.
I don't know. What do you think?
I don't know. Great video, Matt.